Yeah, thanks, Katarina, for a nice introduction, and thanks for having me. It's a very great pleasure to be here. So I spent roughly 5 years at the Amazon office in Berlin, and this view is definitely an upgrade to the white wall I was looking at in those 5 years. So yeah, today I'm going to talk about neural architecture search, and this is more like an introductory talk. In the end, I'm going to talk a little bit about applications and current trends in neural architecture search, but this is very much the basics, essentially, of neural architecture search. Fortunately, I don't have the time to cover all of it, so I will focus what I think are the most interesting aspects. So we will start with what neural architecture search actually is, and then the core components of it, which are the search spaces and the search methods. And this somewhat connects to the talk from yesterday about hyperparameterization. Then we talk about a bit about benchmarking, which is highly relevant in AutoML in general, but especially I think for neural architecture search. And then in the end, talk a little bit about applications of NAS, where NAS, how NAS could look like in the real world, so to say. So let's start with the motivation. So, well, you're all familiar with machine learning, and when you're as old as I am, then when you had machine learning courses in your master degree, it was all about classical methods where you have your features. For example, here you want to classify between different foods, and you define those features like the color, the size, whatsoever, and then you have a machine learning model that trains on those features, right? It's pretty much the tabular data regime that we talked about yesterday as well. But the core point that I'm trying to make here essentially is that the features were you had to define them, right? It was manually work, and the automation and the machine learning was afterwards. Then deep learning came along and it just revolutionized the field, because you essentially just feed in the raw features, and then you learn those features at the same time you learn the classifier, right? So it's what people back then called end-to-end learning, essentially. So there's no feature engineering anymore. Right? This tedious manual work to design those features, you essentially learn it automatically. Now, over the years, there have been multiple types of architectures defined. So this is for image classification. It started off with some convolutional neural networks. Right? This is actually, it just starts here somewhere about 2016. You can actually extend that slide further to the past, where you had Linnet and so on, and then somewhat the deep learning revolution started. Most notable were our REST nets here that achieved a new state of the art back then on ImageNet, and there are I don't know how many papers where they modified REST nets, where they read wide REST nets, where deep REST nets with it. All kinds of modifications in terms of activation functions and so on. And then there were, somehow this pointer is not really working well. This is a mobile net is actually one of the first NAS methods we're going to talk about in a second. And now we are here, vision transformers. Also there are different types of attention, for example, different types of activation functions. So essentially, you change the feature engineering, right? Where people usually try to manually design the features, you change it now by manually defining the architectures. So it's still manual tedious work, but it's not the features anymore, it's just really the architecture. So essentially that happens now on a different level. And the idea of NAS is to essentially extend this idea of end-to-end learning to also automatically design the architecture, such that you don't need to bother around with those manual design choices. Now, how can we define NAS? So this is a generic definition of NAS that you can find in the literature, and sometimes people change it a little bit. But in general, what you're trying to do is you want to define a search space that contains all the architecture, all possible architectures, and you want to find the architecture in the search space that minimizes your validation loss. Now, in order to minimize your validation loss, you first need to train the architecture, right? So we assume that we have a somewhat optimal set of the parameters, which we denote here as W star. And that somewhat resembles, so theta R here is the architecture, essentially. And key part here is the search space, which you're going to talk about, because the search space determines like whether you're going to find like an optimal architecture or not, right? If the architecture isn't in your search space, you're never going to find it. So the search space is a key part here. And well, I also already mentioned the trained parameters. So that means that every time you evaluate a feeder, you first need to train it, right? And this is pretty much, it's very orthogonal to hyperparameter optimization, right? So in hyperparameterization, you have essentially the same function, just that your feeder here are not architectures, those are just hyperparameters. But you also here, you need to train a machine learning model. Just in NAS, you need to train a neural architecture, which is usually much more expensive than, for example, training an XGBoost model or, I don't know, a support vector machine or something like that. And on top, as we're going to see in a second, is that those search spaces, compared to the search spaces that we usually have in HBO, are more diverse, so higher dimension, discrete parameters. So they're more complicated to explore. Now, we can extend this idea of neural architecture search to multi-objective neural architecture search, where you're not just trying to optimize one objective, like the validation error, as you saw on the previous slide, but multiple ones, right? We want to find architecture that performs very well on our validation set, but also achieves, for example, a low latency, maybe on an embedded system, or has a specific parameter count, memory footprint, or which also becomes more relevant as the energy consumption. Now you have those multiple objectives, and they're somewhat competing with each other, right? So usually, you know, the bigger you make your network, the more parameters you put into it, the better your validation error becomes. But at the same time, you also get your latency becomes worse, or your memory footprint increases. So it's a trade-off that you have to make here. So essentially, in a multi-objective setting, you don't have a single solution anymore that optimizes all of your objectives at the same time, right? So because you have those conflicting objectives, you come up with a Pareto font, right? Essentially, each point in this Pareto font here with this dashed line here dominates all the other points in your search space, right? So each point here is essentially one architecture, and we want to minimize here test error and parameter count. So the more we are here to the lower left, the better. But obviously, if you want to minimize actually this is a typo. I think it should be. No, sorry, both minimizing it, so it's correct. But the more parameters you might have a lower test error, but obviously, you know, that objective increases. And in the multi-objective setting, so in order to estimate how well such a Pareto set performs, you still need to quantify that, right? You still need to assign it a metric, essentially. And there are different ways to do that. One of the most popular things is the so-called hypervolume, where essentially you measure the volume of your Pareto font to some reference point, right? And the larger this hypervolume is, essentially the better or the more diverse your Pareto font is. So it's a bit more challenging, essentially, to quantify a Pareto font here. Now, let's go back a step about neural architecture search. So this is the general problem that we're trying to optimize, either in a single objective setting or in a multi-objective setting. And now, neural architecture search, we can, on a high level, separate 3 different components. So the first one we already talked about is the search space. And we're going to see in a second, like, different types of search spaces. Then, given the search space, we have a search strategy that's somewhat orthogonal to what we do in hyperparameter optimization, right? And actually, as we're going to see later, we can also use the same methods that we can use in hyperparameter optimization, not all of them, but some of them also in a new architecture search setting. Then something I'm just going to briefly talk about is the performance estimation strategy. So how do we quantify whether an architecture is good or bad? So far, as you saw in the previous slide, we usually take the validation error if you measure performance. But there are other cheaper ways to quantify whether an architecture is good or bad, essentially. Okay, then let's jump right into it. And the first thing we're going to talk about is search spaces, right? So I already said, so, you know, it's usually a finite set of architectures, and there's a trade-off. You want to be very expressive, right? You want to find a new powerful architecture. But at the same time, if it's too expressive, right, as a thought experiment, if you include essentially a search space that's contains all possible architecture in the world, then it's very unlikely that we find something, or we would need a tremendous search budget to find something that's even remotely sensible. So that's an intrinsic trade-off that we have to deal with. And there are different types of search spaces that have been proposed in the literature. There are macro search spaces. That's very similar to hyperoptimization, right? You optimize the number of layers, the number of units per layer, and so on. So that's very close to hyperoptimization. And then cell search spaces, that's the one we're going to talk about in a second in more detail. And hierarchical search spaces essentially is that you optimize the macro architecture, right, the overall architecture, but also maybe some details of the architecture. And then context-free grammars is also going to be something I briefly talk about. So cell search spaces, it's a very interesting concept because that's also somewhat different to what we have in hyperoptimization, because here we assume that the architecture is a DAX, like a direct acyclic graph, right? So it has nodes and edges. And you can now think of like each node performing a certain operation, like a convolution, and I don't know, attention or fully connected, whatever. And the question is, okay, which operation do you want to perform in each node, and how do you connect those nodes together? And that's the cell essentially. And now what you normally do is you can either think of the architecture as a one big, large cell, but that's somewhat infeasible, right? Because if you think of so convolution neural networks or like now transformers, you have like, I don't know, 20 or 30 layers, so that would quickly becomes infeasible. So what people normally do if they talk about cell search spaces, they have one cell with just maybe 5 or 6 nodes, and then they take the same cell and stack them on top of each other, right? So essentially each cell essentially is one block, and you put those blocks on each other. And they have the same structure, the cells, so you only need to find one cell, but they have different sets of weights, right, that you then learn with just gradient descent. And what, especially in convolutional networks, people do is they actually have 2 types of cells, reduction cells and normal cells. Reduction cell essentially is just the difference is that you first reduce the feature vector before you feed it in there, right? So in convolutional networks, you usually have done like a additional convolution first before you feed the input to the reduction cell to reduce the dimensionality of the feature vector, and then you have a new cell there. So how do a cell look like? So this is, for example, some cells that Soff et al. Found to perform quite well on ImageNet. And you can see it's quite complicated, right? So you have those different nodes, right? So this one here is the separate 3x3 convolution. This is just identity mapping. You have average pooling here. And then you have the different edges. So this is essentially your feature vector that comes in here, right? It goes into this block here and this block here. And then you combine them somehow. And then in the end, you concatenate all the feature vectors and get a new feature vector, right? This is one cell. And this cell you would essentially stack on each other. And the same here for reduction cell. And you can see here it looks somewhat different in the sense that you have maybe different type of less operations here and different types of operations in those nodes. And here also you have actually 2 layers, so to say, right? So whereas here you just have one white layer. This was found automatically by Nash, and you can already see at this one here. So it's much more complicated than like an HPO, right? Because for each block you need to decide which operation you want to perform, and then you also need to decide how to connect those different edges, essentially. What are the advantages of cell search spaces? Well, they're moderately complex in the sense that they're still expressive enough to find interesting new architectures, like this one here. Probably nobody would have come up with this by themselves. But at the same time, they are not too complicated and too high dimensional that we can't find anything anymore, right? There's a bit of back and forth. You can transfer them across data set. That was essentially pitched also in the original paper. But I think Marius mentioned it yesterday, so that only holds to a degree, right? You can transfer them from like Cypher 10 to ImageNet maybe, but if you transfer it to a medical data set or something completely different, then it might be not so transferable anymore. What's also interesting is that you can apply different types of search methods there, right? So you can run, as you're going to see later, reinforcement learning, evolutionary methods, Bayesian optimization methods. It's not quite straightforward, right? So especially in Bayesian optimization methods, you need to do some changes there, but in general, you can run a large range of methods there. What are the disadvantages? Well, I said this model really complex. At the same time, also it's limited expressivity, right? So we're going to find something new, but not like completely new, right? We're not going to find a new transformer architecture, so something that's like totally revolutionizing, right? It's still somewhat limited. We still assume that you do like, you know, convolutions in there or separate convolutions or, I don't know, attention or something like that. But we're not going to find like entirely new operation. Like we're not going to find like the next attention type of thing, for example. Then another thing I want to quickly mention, which I think is quite interesting because this is a rather new direction of NAS, is to define context-free grammars. And that was the paper here by Linus et al., Linus Eriksson et al., called Einspace. And essentially, the idea is that you find this grammar, right? You define this kind of rules. Well, actually, so if you define the architecture, essentially, you define it as a string, right? It's a string where each token in that string essentially determines what kind of operation you want to perform, or how do you combine those different things, right? If you do want a branching, or if you want a stacking, or whatever. And then you define this grammar rules. With your terminals could be then just some different types of operations, like you know, values, softmarks, identity mapping, convolutions, and so on. But you also have ways to combine different types of operation, right? You can multiply them, you can add them, or you can concatenate them. And this type of grammar, where you, as you do with context-free grammars, you define like you derive a tree essentially, right? You start your starting point and then end up in a terminate point. And that is a very expressive search space and leads to very funny, you know, graphs essentially. Here are just some examples of some typical architectures from the literature, how they would look like in this search space, right? So you have a typical ResNet architecture, right, where you have those skip connections between each layers, and you can see them here. So essentially, this is one layer. You perform different types of operation. At the same time, you do also have the skip connection here, right? And essentially, each of those little, what do you call it, circles, essentially is one layer that you tap on each other. Yeah, there's a question.
If we define the search,
yeah. Yeah.
And now you have a description of search space by derivation.
Yeah.
That's missing other information because you would have like 2 or 3 things that into the same graph or the theory that both the set of trees to the set of graphs, because if you easy examples the same tree.
Yeah. Right. Yeah, that's a very good question. It's not just in this space, actually. You also have that in the cell search space, right? It's called graph isomorphism. It's a good question. So yes, that is a problem. So essentially, what you're saying essentially is that different graphs or different encodings of your architectures essentially map to the same architecture, right? You have 2 different configurations in your search space, but they look different in the way you encode it, be it as a here in this context-free grammar or in a cell search space, but effectively they're mapping to the same architecture, and that is indeed a problem in NAS, and there's been some ways to counteract on this, right? So essentially it's an NP-hard problem essentially if you see it as a graph, yeah, people try to essentially, you can't solve it, but you try to combat it essentially by different types of encoding, right? You find a better encoding of your architecture that essentially, that encoding, if it's the same architecture, it's also essentially the same encoding or something like that. We don't have the time to go into this because it's a bit more advanced, but it's a good point actually. This is something that you need to keep in mind if you define those kind of search spaces here. I mean, it's in practice maybe not so much of a problem, right? Because you know, in the end of the day, you do a search essentially, and then maybe a search algorithm figures it out, and it's more like a local search method. But yeah, nevertheless, it is an thing you need to keep in mind if you define those architectures. Yeah. Yeah. So maybe just to wrap up the search spaces. So advantages of those context-free grammar is that it's extremely flexible and it's somewhat easy to make it sure that it contains essentially all the important existing architectures, right? Like the ResNet, VIT, MLP mixer, whatever. That's important because you know, you want to run your search essentially, and if your search ends up in being one of those architectures that are from the literature, it says, okay, maybe that's the best architecture we can find, right? So you want to have like a reference point. Ideally, you find a new architecture that is better, and then you can say, look, obviously this one is better because otherwise my search algorithm would have found one of those reference points. So that's why it's also important to design your search spaces such that it also contains existing architectures. And that's not always possible. It's possible with search spaces, but not so quite as that you contain all the really different types of architectures, right? So you can maybe fairly easily contain ResNets, but it's, for example, more challenging to contain visual transformers at the same time. The main disadvantage at this point, at least, is the searchability, essentially, right? So it's not very easy to search in the search space, and so far people mostly use evolutionary algorithms because they're very flexible. Things like Bayesian methods, for example, so Bayesian transition methods or weight sharing approaches that we're going to talk about in a second, you can't apply them easily in this search space. And evolutionary algorithms are very powerful, but at the same time they're also very inefficient. They require a lot of samples, so it means you have to train a lot of architectures from scratch until you're going to converge to something sensible. And this is very much an active area of research, so you know, maybe in a couple of years I need to update this slide, but so far people only use evolutionary algorithms. And then here, but evolutionary algorithms, you can still like do like more better encodings, for example, such that based on the encoding of your architecture, you rule out those equivalent architectures. And there's a recent paper on this actually at AutoML conference. Right, so about the search space, any questions so far, any comments before we jump into the search methods? Yeah, please go ahead. Yeah, well, I mean, all of them do. So Einspace, I would say it's maybe the most, but I personally find the most interesting recent paper on this. There's some follow-ups on this. And yeah, they in their search space, they contain those existing architectures, right? And they're just some state-of-the-art architectures like visual transformers and MLP mixers. But they show that you can find something even in this super high dimensional space that is performs better than those methods, at least on those benchmarks they look at, right? This is also a bit of a trade-off, so you know, you're only going to find a better architecture on your benchmark. And the benchmarks they look at are, you know, rather small, so simple image classification problems like Cypher 10. We have some bit more interesting problems that are, I think, some tabular data set problems and so on. But they're nowhere close to, you know, something that we use in large language models or something like that. Yeah. Yeah.
So because essentially it's like a complex programming, so every architecture can also be presented as a string. Like
Yeah.
it goes from like on left to right. Can it theoretically be possible to like use some sort of LLM, like just narrative space?
Yeah. Yeah, it's a good question. So what is possible? So honestly, I haven't read the paper. I know the authors and we talked about it, but I haven't read the paper. But yet it just came out like a couple of weeks ago. Is where they take the string and they learn like they use a BERT model, like an encoder-based model, right? So it's a model where you give it just a string and it gives you a feature representation essentially, and then they take that feature representation to do then some search on it, right? So they don't search on the string, which is very complicated, and you can only do with architecture with evolutionary method. But now you get a numerical representation of your string essentially, and then you can run also things like, for example, Bayesian normalization or something like that. Don't know if they do that, but the idea here is really that you essentially use a BERT model, like a small encoder-based transformer model, to learn a numerical representation. That is, for me, a very sensible approach, actually. They're not for this search space, but for those cell search spaces we talked before. There are some approaches where they use graph neural networks. And those, it's also kind of sensible, right? You take a graph neural network to represent this graph as a numerical feature vector, and then it's much easier, right? It's maybe high dimension, but it's a numerical vector, fixed dimension numerical vector, and then you can just run, you know, any global optimization method you like, reinforcement learning, Bayesian normalization, whatever. Yeah, good question. Thanks. Yeah. What? Yeah, that's a $1 million question. So I don't really have a good answer to this, to be honest. So ideally, you as a user, so to say, you shouldn't be bothered with defining the search space, right? Because then we're kind of back in this on the previous slide. So you replace the feature engineering by deep learning to design your architecture, and now you design your search space instead of designing the architecture. So it's a, how do you call this, like a self-eating snack problem. So essentially, yeah, as a user, you shouldn't be bothered to find like your own search space. With that being said, right, it depends on your use case, right? So we're going to talk about later about hardware awareness, where you say, okay, you know, I maybe know good architecture, but I have very specific constraint to deploy that architecture on a specific hardware, like for example on some FPGA or I don't know, some other embedded system. And I don't know how to optimize it there. And then you can define the search space, and you can say, okay, like, you know, you could try this different type of operation here, like attention or the kernel width of my convolution, for example. And then you as a domain expert, obviously you have the expertise to design that search space. Here, essentially, the goal would be to find one unique search space that allows you to find like entirely new architectures, but not something everybody who runs trains their own model needs to design. Yeah, I hope that somewhat clarifies it. It's not a very satisfying answer, I know, but yeah.
One problem that I see is like because time space also comes like fundamental operations, so
Yeah. Right.
and that's the reason
Yeah.
why like the expensive. But also like again, like they really rush to search upon.
Yeah.
What do you think would be like a perfect trade-off in terms of if we want to search for these fundamentally transformer operations, but also like to have these macro values? Because
Yeah.
I've learned about hierarchical search spaces
Yeah.
in this case,
Yeah.
but they're also like not so promising. Like they don't have as much
Yeah.
time space. What
Yeah.
would you say is like the perfect kind of like secret sauce of trade-off?
Actually, can we hold that question? I have a slide later because it's something I want to talk about in the discussion later because it's an important point actually, and yeah, I could waffle around this for an hour. So let's maybe take it later for the discussion. That's okay, thanks. Because it's a really good point, and I want to talk about it later more in a general context of math. Any other questions? So okay. So okay, this is the search spaces. So now the question is, so how do we search in the search spaces, right? This is another the big question. And the first obvious approach, I'd say, is, well, we call it black box optimization. You could also just call it gradient-free optimization or HPO, because effectively what we do essentially is hyperparameterization, right? It's a special case of hyperparameterization where you just optimize hyperparameters to continue defining your architecture. So here we essentially assume that the search space is somewhat a discrete set of architectures that we can search through. We can define it as a simple search space to run our HPO methods on it. And we assume that we train and evaluate each architecture independently with a separate set of weights, right? It's essentially HPO, as you saw yesterday in Bernd's talk. And I want to just talk about two methods that are quite popular, and if you Google NAS, for example, you're probably going to find those papers. So whether essentially the initial papers by Google that essentially triggered this entire NAS hype in 2016. The first one is a reinforcement learning approach by Soft et al. The idea essentially is you have a controller network. It's a small feed-forward network with 2 layers, I think, maybe more, but something like that. And you train this network with reinforcement learning, right? Just reinforce. It's one very simple reinforcement learning approach. And you reward essentially that controller network that samples architectures, and you validate this architecture, you get a validation error back, and you take that essentially as a reward for your reinforcement learning method. And back then it was quite successful. As I said, started the NAS revolution by achieving state-of-the-art performance on Cypher 10 and PTB, which is an NLP data set. But at the same time, it was also extremely expensive, right? They ran it, I think, for 2 weeks on 800 GPUs, which, in 2016 is something else than in 2025. So it's still a lot these days, but nothing that seems so far out of reach than back then, right? So when I was still a PhD student, I was like, yeah, okay, never going to run anything on 800 GPUs. Now we would be probably able to do that, but still somewhat overkill, right? Cypher 10 and PTB, even back then it was somewhat toyish benchmarks. So here's another visualization how that looked like, right? So you have this controller network. Actually, it's a Recon network. Sorry, I said an MLP, but it's a Recon network. You sample an architecture from it, as you're going to see in the next slide. You train this network or this architecture with its own sets of weights, and then you compute a gradient based on this reward function. And the way you sample from it, essentially you sample each operation at a time, right? So the number of filters, for example, the filter height, filter width of the convolution network, and so on. And you have this anchor points that essentially to allow script connections, right? How do you connect the different layers with each other? And if they, back then, because it was so expensive, they just compared it against random search. Here you can see essentially the improvement upon random search. And essentially, if they just take, this essentially determines how often they update the controller, if they take 15 models so, to compute a reward function or just one model. And this is extremely expensive plot because essentially they trained, each iteration essentially is training one architecture. And yeah, they had to parallelize it quite substantially. Now, as we're also going to see later, this is actually highly inefficient reinforcement learning. And other approaches like Bayesian normalization or evolutionary methods and so on, they usually tend to perform much more efficient. But the paper still had made quite a big splash actually. Then almost at the same time, maybe 1 or 2 years later, there was another paper by Google by a different team where they used an evolutionary approach, right? And it was actually a very simple approach. You just have a population of architecture, so just think of it as a set of architecture that initially is sampled uniformly at random from the search space. And then each iteration, you pick one of those architecture from your population, you mutate it, and then you evaluated it, and then put it back in your population, and you only throw away the oldest element from your population. So that's what makes it very simple, right? So you don't have a somewhat more complicated evolutionary method that does some sort of tournament selection or whatsoever. How do they mutate it? So essentially, you randomly sample one operation or one edge, right? So you can either sample an edge or you can sample one operation from your architecture, and then you just flip it, right? So in the case of edges, you just remove it, right? It's a 0-1 encoding essentially, right? So it's either active or not, and you just flip the bit essentially. And for categorical values, you just sample a new category, right? So for example, here in that node here, you have an average theta-Williams convolution, it's just mutated by doing a skip connection. We don't perform any operation essentially. So it's very simple method, but it performed actually quite well. And while here they ran it actually also on Cypher 10, and they started in the initial population was a very simple method, simple architecture, right? You just have your input, you just do one global average pooling, and then you have your output. That's actually the most simple architecture you can think of, right? And then they ran it for some time, and you can see here this it found after I think roughly sorry, the plot is a bit capped here, but I think it was roughly about 70 hours. They found an architecture that looks like this. You can see it's always much more complicated, right? This looks like a typical convolution neural network, right? So each C here is a convolution with batch normalization. I have also some skip connection here. And then later, after 200 hours or something like that, that's I think the optimal architecture they found on Cypher 10. So you can see that's quite an improvement, right, from the most simplest architecture in the beginning to this thing here, which looks like much more complicated and not necessarily something that you would have come up with as a human. But still, it contains some things we know, right? So it stacks those different convolutions on each other, it has batch normalization and so on. Somewhat interestingly, it doesn't do much of skip connection, but that might be because of the benchmark on Cypher 10, so maybe that doesn't help so much. So those are evolutionary methods. I already mentioned batch normalization. I don't want to go into details here because you heard about batch normalization yesterday. But essentially, we can also run classical methods like TPE and SMAC. Actually, as a matter of fact, which is interesting, the TPE paper, so Bergstedt, they had another paper at ICML, I think, in the same year, where they run TPE on essentially, but they didn't call it neural architecture search back then, they called it model search, I think. But for me, that was essentially the first NAS paper. And back then, but it was a much smaller scale, but still they actually found new architectures on, I think also Cypher 10 with TPE. It's a really cool paper. Yeah, SMAC I already mentioned, so then we can also run Gaussian process-based methods there, but here we need to be a bit more innovative in terms of modeling the objective function, right? Because we have this high-dimension discrete space, so we can't just easily model this with a Matern kernel or RBF kernel. So we need to be a bit more clever how to model essentially the correlation between architectures. There are different approaches in the literature. So for example, Bananas by White et al., they use a specific encoding of the architecture. NASBot was actually quite interesting. They came up with a new type of kernel based on optimal transport, right? You have essentially, they encode it as graphs, as two graphs, and then they use some optimal transport method to map, to measure essentially the correlation between those different graphs. And some similar spirit was this paper by Robin et al., who used a specific graph kernel. In general, so I think Bernd talked about it yesterday, so we can, since we essentially in HBO land here, we can also use all the advancements of HBO, like multi-fidelity optimization, transfer learning, and so on, to also accelerate NAS here. It is then essentially an HBO problem. Yeah, so some of the advantages of the spec-based methods, I already mentioned that, right? So it can be applied to different types of search spaces. And as I just said, we can reuse advances from HBO. But the big problem here becomes quite quickly infeasible, right? Because you need to train each architecture from scratch. And even if you do something like multi-fidelity, HBO, transfer learning, whatsoever, you still need to train a few architectures. And if you think of, for example, the transformer architectures now, or the kind of models that we train these days, even training a single architecture is extremely expensive. So those methods, they really only work, at least as of today, on moderate-sized architectures, right? If you want to go really big, then it quickly becomes somewhat infeasible. And there are some interesting directions right now, and I'm going to mention a few of them in a second, but as of today, it's still like, it wouldn't really work in a LLM setting, for example. Yeah, before we go to the next setting, any questions about black box methods? Yeah.
I understand how you can make a solution to these problems, but how you actually find out what you got survival in drugs.
You mean to get like the GP model? Yeah. Well, I mean, essentially, there's just a kernel method, right? So how you define the kernel, essentially, and they call this Weisfeller-Lehmann kernel, I think.
Yeah, sure.
It's called in the graph literature.
But how do you optimize the circuit?
What do you mean?
You still have like this third space of like.
Oh, I see. So you mean how you optimize the acquisition function, essentially? Yeah, okay, gotcha. Yeah, well, for that, you just can then run the an evolutionary method. Okay. That's the most simple approach, right? You just run some evolution. I think that's what they did here in both of these papers. I need to look it up again, but I think they just ran some very simple evolutionary method. You know, evolutionary nice thing is they're very flexible, right? They work it's very easy to get them to work on a search basis. But as I mentioned, they're infeasible. But since you here just optimize the acquisition function, you can afford that, right? You can just let them run for a little bit because it's fairly cheap. You just need to optimize the acquisition function. Yeah. I'm not aware of anyone trying to get it to work with some gradient-based methods or something. I just think it's really worth the. You can just even run local search, right? You don't even need to run an evolutionary method. Yeah. Yeah. Oh. Yeah. Yeah, you mean, for example, here in this setting, no, sorry, skip this slide. Right, so you have an existing architecture, you mutate it, and then you would train it from scratch, but at the same time, we want to, okay, could I just not reuse the checkpoint as well from the, yeah, a good question. Yeah, yeah, so actually there is some work on this already back then by, for example, Thomas Elsken. It's not so trivial, right? Because, for example, if you change, well, I mean, here you add the new edge, right? For example, and then you change the input to your features. Okay, and that one might even work, right? You could just add this to your graph. But the question is essentially, if you change the mutation here, for, the operation here, how do you initialize those weights, right? So and there's some ways to do that. It's called net to net, essentially, where you perform a certain operation to make sure that essentially your function is that the models is preserved. But that's not trivial and doesn't work with all the search spaces. And there was some work in this direction, but my personal view on this is it seems very, sensible, but in practice it's actually really hard to get it to work because it gets brittle very quickly because you can only allows very specific operations and so on, and yeah, that just makes it not very robust essentially to work reliable in the real world. At the same time, somewhat interestingly enough is that you might need to train it a little bit longer so that it adapt, right? Because you change your operation and maybe change your so you need to train it then a little bit longer, and then you don't gain so much more anymore with in terms of efficiency and in terms of search speed, right? Because you have to change your model longer. Yeah, with that being said, right, so there's some work in that direction, but so far I personally think it's not really dominant in the literature, or hasn't been picked up so much anymore. Yeah, but good question. Yeah, thanks. Any other questions? Okay, let's move on then. Sorry. So the next thing I want to talk about is weight chain based NAS, and that's it's a different type of search method essentially, but it's a radically different approach than the type of black box methods that we looked at. The idea essentially is that instead of training multiple networks that we either sample through evolutionary methods or Bayesian normalization or reinforcement learning, we just train one network. And that one network, it's called a super network. It's a super network because it contains all possible architectures in your search space, right? So as we see in the previous slides, at least in the cell search spaces, you have a finite set of architectures. It's maybe very big, right? So it's maybe a few, I don't know, million of 10,000s of architectures, but it's a finite number. And so it's possible to essentially define one really big ass network, and each path through this network essentially corresponds to one architecture in our search space. Now, the idea essentially is to train this one big network with just gradient descent whatsoever, and then you sample graphs through that network, and each graph essentially corresponds to one architecture, right? And those are called subnetworks. So one approach that was actually quite popular in the literature is called DARTS, where essentially we are in the search space again, and now instead of in the nodes, we don't perform. So operations are not performed in the nodes. Operations are performed at the edges, right? So essentially, for each edge, we have essentially 4 or 5 different types of operations we could perform, and then in the nodes, we just combine those feature vectors from those edges. And in each edge, we just want to eventually select one operation, right? And then in the nodes, we just concatenate them or average them or whatever. And the way that does it is essentially to define like auxiliary parameters or architecture parameters here called alpha, that it's a continuous parameter for each edge. So think of it essentially as of a weight for each operation, right? And then we can jointly optimize those parameters together with the weights via gradient descent. And then in the end, we have like each edge has a different weight, and they just take the argmasks. And that gives us a final architecture. And then what that does, it takes this architecture, and that one is then trained from scratch again. So those are the 4 different types of phases, essentially. And maybe most importantly is this part here. So, if you remember back the first slide where we defined the problem definition, right? We have the argmin of alpha of the validation loss, essentially. What it corresponds to is a bi-level objective problem, right? In the linear objective, we just have our standard training loop where we minimize the training error with respect to the parameters of our network. And then we have this outer loop where we minimize the validation error with respect to our architecture parameter. It's the same thing here in DARTS, right? So you have this bi-level objective problem. And you could do just gradient descent on that, right? But every time you do a gradient update in the outer loop means you need to do like a full optimization in the inner loop, right? You first need to train your network, come to gradients, you need to backpropagate essentially through the entire training process, and then you do an update in the outer loop. Actually, this is something probably hasn't been mentioned yet, but also exists in hyperparameterization. It's called gradient-based hyperparameterization or online hyperparameterization. The problem here is really like you need to backpropagate essentially gradient through the entire inner loop of your training process, and that's quickly infeasible. So what that does is essentially they call it alternated optimization, I think, where you just do a single update step in your inner objective, right? You just take a network, compute gradients, update your weights, and then you optimize the outer objective. So you alternate between the inner and the outer objective. You can say that's some sort of an approximation essentially of it. And then it becomes actually feasible again, right? Because then it's not much more expensive than a single training one. It's a bit more expensive, but not a lot more. But at the same time, you make a very strong approximation there, right? Right, and that's essentially the I would say the most novel part, maybe not the most novel part, but a key part here of DARTS to make it actually work. At the same time, well, honestly, I want to be honest with you. So I'm not a big fan of DARTS because there are also several problems with it. The first one is that solution found by darts, right? So the final architecture you find here, it's not so much better than if you would just take a random architecture from the search space, right? So it's a discrete space, you just sample one architecture, you train it, and then if you average it across data sets and so on, it turns out to be not much better than the solutions that are found by darts. That's one big problem that has been pointed out in the literature. Another one is that it's very prone to the random number generator, right? Because mostly because of this optimization here, if you run it multiple times with a different seed, you will end up with vastly different solutions essentially. And what's also been pointing out that you need to invest a little bit in the regularization of your objective function of your optimization problem, such that it converges essentially to actually anything sensible, right? Otherwise, you find some trivial solution where all nodes essentially skip connections and so on, and without that regularization. And yeah, as I said, I'm personally not such a big fan of it, but it made a bit of a splash, and actually there's still papers being written on it. At the same time, there's this nice German word, Bärendienst, so where you try to help something on, or help somebody on something, but it turns out that you're hurting them more than you're actually helping them. And I feel like that's the same with darts and NAS, to be honest, because it created quite a bit of interest, and there are like a lot of follow-up papers on it. But at the same time, people are kind of looked at it and said, hey, this is not going to work. And they tried it on their application and said, hey, this is not working at all. So NAS is stupid. But I think it's a more problem of darts, not so much about NAS in general. Maybe before we go to the next weight sharing method, any questions on darts? Any comments? Yeah. 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 Yeah.
You can like approximate something as good as the other way by small
Yeah.
architecture. So if you
Yeah.
want to make a non-trivial
Yeah.
search problem,
Yeah.
you should put some count on
Yeah.
the size, because otherwise I've seen that you can
Yeah.
say, okay, by when it's something
Yeah.
big enough, I always
Right. Yeah. So couple of points there. So actually, it's yeah. Thanks for mentioning that. So first of all, as we're going to see on the next slide, so there's a different type of weight sharing approach, and that's much closer to pruning, right? What you're saying essentially with lottery tickets is that you have this big network and it contains a certain amount of smaller networks, and if you're essentially lucky, then you can find like a small network that maintains the performance of the entire network, right? Just as part of the network. Essentially, that's for me a bit also the motivation for the next approach, two-stage NAS. And as we're going to say, the leader application, so I think that's where also NAS can be interesting as a type of pooling approach, right? So you say essentially, you take your network, you see that as a super network, and then you want to find like a sub-network in that super network. There's one thing, and we can talk about it later when we talk about model compression, that we should keep in mind is that lottery tickets operate on a weight basis, right? Here we operate on an architecture base. So it's a difference between unstructured pooling and structured pooling, right? You can remove single weights, or you can move structured components like layers or, I don't know, different nuance, right? So essentially, if you think about in your network, what it is, essentially it's you stack multiple matrices together. Now you can remove single entries of your matrix, that's the lottery hypothesis, or you can remove entire columns or rows, and that would be like a structured pooling approach, what NAS would be doing. But then maybe let's talk about it in more detail when we get to the model compression, because then maybe it becomes a bit more clear what I'm trying to say here. Yeah, actually, any other comment on that before? All right. Yeah, go ahead. Yeah. Yeah. Well, I mean, what I mean when I talk about darts, I actually mean more like in general those gradient-based methods. So they often call it darts approaches. Yeah, I think so. Parts of it comes from this guy here, right? I think the approximation here is not particularly good. Another part also comes from this stuff here, but this has been somewhat addressed in the literature. So I'm going to talk about two-stage approaches later, but there are also one-stage approaches, and that's more like a darts approach, where essentially you don't do this retraining from scratch. You just end up with a final architecture, right? So essentially skip this step here, because going from here to here, this is actually causes another big of a problem, right? Because you find the optimal architectures for this specific set of weights, but now you take it architecture and train it from scratch with a new set of weights, and then it turns out to perform not well anymore. So current papers essentially they don't do this step anymore, and that's why it's called then one-stage approaches, and that combats some of the approaches that you have in darts. But this one is still is there, right? And it requires, you need to be very careful with it and need to do some regularization and so on in order to work. Yeah. Okay. Then yeah, let's move on. So another type of approach is called, which is also weight sharing, where it's called two-stage NAS, and that's actually, I think, a much simpler approach, and my personal view also performs much better in practice. And the idea essentially is to train the super network, right? But you train it just with gradient descent, right? It's nothing, but it's a bit more complicated than vanilla gradient descent, as you're going to see in a second. But essentially, you just train it like you normally train your super networks, and then you can run black box search on it. You find a subnetwork in that super network, and then this black box search essentially it's the same stuff that we talked about on the previous slides. Just that every time you evaluate an architecture, you not train the architecture from scratch anymore. You just take a subset of the shared weights of your super network. And that so it becomes very cheap, essentially, right? Because there's no training involved anymore. So how does it look like? So here's a very simple example. So here it's a super network where we just assume we have 4 different hidden neurons, right? And this super network here contains essentially 4 different subnetworks, right? So here you just take this neuron, here just take the first 3 neurons, essentially. There's actually a second one, we just take the first 2. I skipped that because the slide was otherwise too full. But you see the point, right? So you have, if there's 4 neurons, you automatically get like essentially 4 different subnetworks. Whereas one subnetwork essentially corresponds to your super network, while it has all the neurons. So your search space here in this case essentially is just the parameter between 1 and 4 that determines the number of neurons that you have in there. Now the idea essentially is to train this from here with gradient descent, and then you just take a subset of the weights, evaluate it, and see how it performs. And there's this concept of weight entanglement, because essentially, you know, if you train the super network, you train all the weights at the same time, right? But then later on, some weights end up in your subnetwork and others don't, right? So essentially, the weights of your subnetworks are entangled with each other. And that's something you need to take into account, because if you later remove them, they depend on each other, right? So they assume that they get, so from the output neurons, they assume that they get the input from all those neurons here. So that's something you need to take into account in your training process, that you make your network essentially more prunable, such that if you remove entries later, that it still performs well. In order to do that, you need to adapt your training process. Right, so this is vanilla gradient descent. You all know how that works, right? You just compute in each update step, you compute the gradient of the entire weights essentially, and then the gradient, and then you just update your weights, right? Now in super network training, essentially you need to change that slightly by such that in each update step you don't update the entire weights anymore. You just update a sub part of the weights, and that helps you to disentangle those weights a little bit more, makes it more prunable essentially later in if you do this black box search. And the most simple way to do this essentially it's by just in each update step you sample a random architecture from your search space. Right, in this toy example that we showed before, you just sample a value between 1 and 4, and then you just update the weights of that subnetwork here. Now, this is, as I said, this is the most simple way. This is called random sampling, but there are more complex methods out there that essentially makes it a bit more reliable, essentially. Most notable, if you look it up in the literature, is the sandwich rule, where essentially in each update step, you not just sample one random subnetwork, you also sample the smallest subnetwork and the largest subnetwork in your search space, which is essentially a super network. And for each of those networks, you come to gradient and then you average them together. So that essentially means you have, in each update steps, you do multiple forward paths and aggregate those gradients. So it adds a bit of overhead in your optimization process, but yeah, in practice works much better than random sampling. And then another thing is called in-place knowledge distillation. Here, essentially, the idea is that you somehow regularize your subnetworks, that they are closer to the predictions of the supernetwork. So the idea essentially is that you first do a forward path through your supernetwork, you get your lodges back, and then you do a forward path through the subnetwork, you get also lodges of the subnetwork, and then the loss function that you compute is not just the training loss, but it's the Kullback-Leibler divergence, so distillation loss essentially between the supernetwork and the subnetwork. The nice thing is you can do this essentially in place, right? Because it's just one forward path through the supernetwork, but it helps essentially a subnetwork to be closer to the predictions of your supernetwork. And how does it look in practice? So this is a very simple toy example that I ran on MNIST. Essentially, it's again this same toy problem that we saw before, where we have a single layer MLP, and it has like I think up to 128 different neurons, and the number of neurons essentially is your search space, right? So you have a one-dimensional search space with an integer parameter that goes from 1 to 128. That means you have 128 different architectures in your search space, and the blue ones is I train each one of them in Scratch, right? It's a simple thing, so I can do that. It's a toy problem. In practice, you wouldn't be able to run do an exhaustive search in your search space. But this essentially gives you somewhat the ground truth, essentially. Now, if you would just take the largest network, right, the super network, train it with SGD, and then take each subnetwork out of the super network, then you would see this red diamonds here. And you can see performance degenerates quite quickly, right? So it's got the same performance for the large network, but once you go to smaller networks, essentially performance quite badly. Now, here I do the same thing, but I train it with the sandwich rule and sandwich rule plus in-place knowledge distillation. And you can see it's much closer to the performance of the original networks than if you would just do this SGD training. It's not perfect, right? You still lose a little bit here, but keep in mind, here we train one network, and here in the blue ones, we would train 128 networks. So it's tremendously faster. And even though you lose a little bit, essentially it's on larger networks still feasible by. Yeah. And this in-place knowledge distillation, it adds a bit of, especially for those networks, it makes it a little bit, improves the networks a little bit compared to just the sandwich rule. Yeah, and then once you have the network, essentially you can do one black box search on it. It's the same slide that I had before, right? Just that now W star is just replaced by a subset of the shared weights. So essentially now, every time you evaluate this function here, you don't actually need to train the network anymore. You just take the already existing weights, and then it becomes cheap. Then it's just a single pass over your validation data. And you can run whatever you want, right? Based out evolutionary methods whatsoever. Any questions on that front here? Yeah.
So when you talk about a super network, like it's basically a combination of all the possible networks that exist in that space.
Yeah.
But isn't it a bit restrictive in a sense, because like the connections that are in the super network, that were like it's kind of like a domain. It's like only the connections that are possible in the subnetworks, but only the connections that are already in the super network.
Yeah.
And so does it limit the expressibility of the search?
Yeah, it does. So this type of approaches wouldn't work, for example, in some, at least now they wouldn't work in a like this Ein-space search space we talked about, right? So it works quite well in those search spaces where you have maybe potentially very large number of architectures, but not like a tremendously large number. And you're still somewhat bounded by your super network, right? You still need to load that into memory and so on. So you can't just go arbitrarily large. And it is somewhat, it's somewhat, there's a disadvantage of those methods. They're somewhat limited to moderately sized search spaces in some sense. And you're bounded essentially by the size of your super network. If that doesn't fit into memory, or if that's just infeasible to train because it's way too big, then you can't apply those methods anymore. Yeah, that's true. Yeah.
So when you mentioned that from the supernet, so I
Mm.
like to have like a default fully connected reference point and just say I want
Yeah.
a super network, so I pick the input in the output layer,
Yeah.
and I take
Yeah.
the maximum number of bit layers and
Yeah.
the maximum
Yeah.
numbers of new space
Yeah.
layers, and I put super network,
Yeah.
and then I take the subset. But if
Yeah.
I cell, there is
Yeah.
search space for
Yeah.
where I put
Yeah.
different types of layers.
Yeah.
And I would get so if everything
Yeah.
is the same type
Yeah.
of layer, I see that you can construct the super network.
Yeah. What?
Type of layer is
Mm.
really long.
Yeah, but you would actually train each of those edges in parallel, right? Right. So if you're in the cell search space, or let's say okay, you do. Sorry, let's say you do different operation in each node, right? And you just copy the nodes. You don't just have one node. You have actually 5 nodes, and train all of 5 of them, and then you pick one out of all those 5. Yeah, that's how we would do that in the cell search space. Yeah. 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 Yeah, that's what I meant. You're limited by the size of your super network, right? So you can't go arbitrarily big because at some point your network is just way too big to train. So yeah, that's the limitation I was referring to. Yeah, yeah, yeah. But it's still, I think, what their approaches, for me, they're like a different type of pruning approach essentially, right? And that's where I think there things are getting interesting. And as we see later, right? So when you already have a pretty big network, like in a large language model, and now you want to compress that model essentially. But we talk about it in a second. So okay, I need to hurry up a little bit. So yeah, so there, I briefly mentioned it in the previous slide. So performance estimation is another big topic in NAS, where you try to estimate the performance of an architecture, and so far it was mostly by training it from scratch. But there are also other approaches like learning curve extrapolation, right, where you don't train this thing until the end in convergence or something, you just train it for a little bit, and then you have some extrapolation method that extrapolates, okay, how well does that method works if I would train it longer. That's coming also from HBO land. And then another approach is called zero-cost proxies, which is also a very interesting approach. Essentially is that you compute some statistics of your network, right? So the most simplest one would be essentially the weight norm of your gradient of your weights, and then you optimize those proxies instead of the validation performance. And they're called zero cost because essentially you can compute them without any training. I don't really have the time to look and talk about this, but if you're interested in that, I really recommend you this great tutorial by Jovita and Gabi from the AutoML conference last year. Okay, next thing I want to talk about, because I think it's very important, is benchmarking. And we talked, I think, benchmarking, we talked about it yesterday. It's a major role in NAS, but actually it's a major role in AutoML in general, because it's very empirical driven field, and there's some bit of theory, but it's mostly experiments, empirical science that drives this field. And when NAS came along, right, the initial papers, there was a bit of a reproducibility crisis in the sense that, for example, the paper by Google that we mentioned before, nobody was able to reproduce that, right? And especially for academic labs, it was a bit of a problem to get our papers in because we couldn't compare against their method because we weren't able to reproduce them. But proper benchmarking is the science in itself, and it's, in my view, highly underappreciated, and Kata can probably tell more about this, because it's not trivial, right? So single training one's extremely expensive, especially in NAS. There's a lot of noise in your benchmark that comes from the training itself. You know, mini-batch sampling, random initialization, the randomization of your algorithms, and so on. And then there's a tremendous amount of confounding factors that you need to be taken care of. Implementation details, right? Hyperparameters, because each, you kind of ignore them here, but all of those networks also have hyperparameters that you need to optimize. How to pre-process the data and so on. Now, one trend in AutoML, which I think really helped the entire field to progress, is this idea of surrogate or tabular benchmarks. And the idea is very simple, right? You create a data set by training and validating ideally all of the architectures in your search space. And then you can just, every time you run a NAS method on your benchmark, you're not actually training this architecture, you just look it up in the table. And that essentially then becomes, it's not free, it's still, it's not entirely for free, but it's tremendously faster than training it, than actually running the actual benchmark. And you can extend this idea, and that was originally proposed by Katharina, by surrogate benchmarks, where you not just sample all of the architectures in the search space, but just a subset of them. You fit a regression model, and then you take the predictions of the regression model essentially to predict performance of unseen architectures. And if you look at papers nowadays, I think all of them are using those kind of approaches there, not just in NAS, but also in HBO. But I want to quickly talk about 3 different benchmarks that are very prominent in the literature. The first one, that was work done by us together with Google, where we essentially defined a cell search space for convolutional neural networks. It was had 7 nodes and 3 different operations, so it's actually a fairly small search space. But nevertheless, so we evaluated all of them, and it led to more than 400,000 different architectures. That's also the reason why we joined forces with Google, because we weren't able to train this ourselves. But Google did, and essentially each architecture was trained 3 different times, and we compiled it into one big table. Interestingly, the decision of design for search space was a bit challenging, because 7 nodes and 3 operations is not a lot, right? And even though it's a lot of architectures, it's a very small search space actually, and we even had to constrain it further by just allowing a maximum of 9 edges. There actually more edges would have been possible, but then the number would have been exploded. And we want to make sure that the search space is still powerful enough that it contains architectures such as Inception or Westnets, which were back then state of the art. So this is how it looked like, right? So as I mentioned before, we stacked those cells together in 3 different blocks, and each block had 3 different cells. And as I said, so we had like 7 different nodes, right, and 3 different operations. One was 3x3 convolution, 1x1 convolution, and max pooling. And this has the cell of an exception architecture, for example, how it would look like in our search space. This one was the one we found was the optimal in this entire search space. Yeah, we did some additional things like projection and so on, but I'll skip that here. And here you can see essentially a scatter plot of all the different architectures, right? So all 400,000 architectures, accuracy versus the training time, or the number of parameters. And you can also see like some of the existing architectures like ResNet and Inception. They still perform quite well there, but they're not the optimal architectures, but they're somewhat close there. And then we can use that to run essentially thoroughly compare different optimization methods, right? Which we weren't able to do back in that then before. And we run like regularized evolution. That's the one we talked about earlier, right? This evolutionary method. Reinforcement learning, we also talked about that. And then a range of Bayesian normalization methods like SMAC and TPE. And here you can see that reinforcement learning, I keep in mind this is no logarithmic scale, right? So I don't know, 10 to the 7 seconds, how much is that? It's a couple of weeks, I think. So this is the amount of time it would have taken if you would run the original benchmark, right? Here it took me like, I don't know, a few hours on our CPU cluster to generate this plot. And you can see that reinforcement learning, so this is the average of 500 different runs, so you get a pretty good estimate of your mean performance across seeds, right? And reinforcement learning, this gap seems small, but keep in mind this is a logarithmic scale, so it's a lot less sample efficient than revolutionary methods and base-up methods. There's not a big difference between BO methods and evolutionary methods. And I still think that's maybe now it's a bit better. But yeah. Then this idea has been extended to NASBench 2.1, where essentially it's an even smaller search space than NASBench 1.1, but they don't have this additional constraint in the number of edges, because that is a bit tricky to model actually. And so they had just 4 nodes and 5 different types of operations. But the nice thing here is they evaluated all of those architectures on 3 different benchmarks, right? We just trained it on Cypher 10. They also trained it on Cypher 100 and ImageNet. And this is how it looks like, right? So you have this different types of operation. So serialize, essentially don't do anything, skip connection, different types of convolutions and average pooling. It's also smaller architectures. But this is maybe by now, I think, a bit more popular, and this is benchmark people still heavily use in the literature. And then more recently, by Aber and others from Freiburg, they created NASBench 3.01. That's essentially the first one that uses a surrogate model rather than a tabular model. And the nice thing here is that they can allow for much larger search space. And what's interesting also in the paper is that they actually show that the surrogate models, even though you have like a regression model essentially instead of just table lookups, it turns out to be that they are more accurate than those tabular benchmarks. So you can see that here, right? So they try to approximate essentially the true performance with respect to the number of architectures on this NASBench 1.1 data set. And if you, after a certain degree of architectures that you feed to the surrogate model, essentially performance gets better, and the surrogate better approximates the true objective than the tabular model. So this is something, because there's always a bit of pushback on the surrogate models. People say, yeah, hey, this is noisy and it's approximate and blah, blah, blah. But actually, if you get enough data, then it's a pretty good approximation. Okay, I want to go quickly to the applications, and maybe we can have questions afterwards. Because I think this is more like, okay, you know, we talk about red NAS, but what can we use it for actually in the real world? And essentially, I personally think there are 2 different directions which I think are very interesting and relevant. And the first one is hardware-aware NAS, where the idea essentially is you want to find not entirely new architecture. You have maybe a good architecture, but you want to specialize it to a certain device, right? It could be a mobile device, could be like deploying it on a web server in a cloud environment, or some other tiny AI type of module. Right? You have a specific hardware, and you can show in this paper here, for example, once for all paper, that on different hardware you obviously need to have different architectures, right? And so here the important bit essentially is not that you optimize performance, but also other hardware metrics like the latency on your embedded system, for example. And this once for all network that uses this 2-stage approach that we talked about, right? They train one big network, they call it once for all network. Now people would call it super network. And then they search for the best subnetworks for the different hardware devices. So the black box search essentially becomes a multi-objective setting. And they show that it actually outperforms some other manually optimized architectures like this MobileNet type of architectures. Yeah. Yeah, here, so that's why they call it train once, get once for all, right? So you train one super network and you get like the entire Pareto front of subnetworks for free, essentially, instead of training each one of them for in isolation. More recently, we released a benchmark for decoder-based large language models based on the GPT-2 family. It's still like smaller networks. I think we went to only up to 1 billion parameters. You need to be a bit careful if you, in those benchmarks, in those hardware development benchmarks, how you approximate the latency energy, right? You can't measure it on your hardware device directly because deploying it on your hardware device might be very complicated. So what people usually do is they have some sort of surrogate model that approximate the latency and energy. And we show in the paper that this is not quite trivial because you have quite a bit of noise. Actually, I have a slide on a second on this. Maybe quickly on the search space here for the transformer architecture. So this is more like a macro search space. It's more like a hyperparameterization search space, where you have the number of layers, and then just the width and the number of heads for the attention layers and the fully connected layers. and also the embedding dimension. So it's not a cell search space or anything like that. It's a very straightforward search space. Yeah, and this is what I talked about, the latency estimation, right? So this is for a single architecture. We measure the latency. I don't know. I think we measured it like 50 times or something like that, and then plotted this this KDE to approximate the PDF. The point here essentially is if you measure the latency and you just take the mean, for example, it's not a valid approximation because you have this bimodal distribution here. So that's something you need to take into account, that you have a higher amount of noise essentially, or maybe sometimes also a bit multimodal distributions in your observations. Right, so you can see the Pareto font essentially of these benchmarks, right? Perplexity versus latency, and but with respect to the energy, but I think we have the same plot also with number of parameters. What you can see here is like, yeah, if you just care about perplexity, then you could just go as big as you can with those large language models. But if you take latency into account, the picture changes, right? And it gets more diverse. And it's a Pareto font, right? You can't say that one point is better than the others because all of those points in the Pareto font are dominating each other. And depends on your use case, which solution you want to pick, right? So maybe you're willing to solve something on perplexity because maybe latency is what's important to you. Maybe you even have a hard constraint. You say, okay, anything that's below 200 doesn't work for my use case anymore. And then the optimal architectures that are above there, they don't work. So optimal in terms of performance, they don't work for you anymore, right? So it's a much more nuanced picture here. Yeah, then the second approach, which was already mentioned before, is this pruning type of approach, right? You have a pre-trained network, and now you want to compress it. And you can see that as a neural architecture search problem where you see this pre-trained network as a super network. And now you want to find like a sub-network on it, right? To prune it essentially. Ideally such that it maintains performance as much as possible. But as again here, it is actually a multi-objective problem because there's this natural trade-off between model size and validation error, right? You can't, if you throw away things, then you lose in validation error. And there's a bit of a sweet spot maybe, right, where you don't end up with random performance, but still you're small enough to be, to give you actually any benefits in terms of latency. Yeah, I'll skip this part here. Here maybe just, we tried this, for example, on encoder-based networks on BERT, where we trained us different type of super network training strategies. Right, this is just standard SGD, and each point here is this hypervolume, right, that we talked before, right, that measures essentially the quality of your Pareto font that you find. And you can see that super network training strategies to help you tremendously in order to find better Pareto fonts essentially. And just vanilla SGD is not going to cut it. Yeah, here we compared against different pruning. I'll also skip that. This is then, yeah, also here we actually measure it on latency on the real device, like different GPU types essentially. We also compare the quantization, right? You could just also take the model and quantize it, but that doesn't give you a Pareto font, and often also you lose in performance. This is also interesting because this is in a real-world setting where we prune like one of those BERT models to get the Pareto font, and then we actually take those two models, so the unpruned network and two pruned versions of it, and actually deploy it on an endpoint on SageMaker, and then measure the response time of that endpoint, right? So we essentially send it queries to it and measure how long it takes, how long it takes to respond. And you can simulate it with different number of users, and you can see that by pruning the network, you tremendously cut the response time. And here the solid line essentially is the median, and the dashed line is the solid line is your median, and the dashed line is the mean. And you can see here that it at some point diverges. And that is some throttling effects that we see with SageMaker. So the point essentially is that this pruning actually helps you to really reduce the response time of your system. Yeah, if you're interested in more, there's a blog post that we wrote when I was at SageMaker. This can be also scaled to larger models with LoRa, provide efficient fine-tuning types of approaches. And actually, we tried this with a Llama model where we compared against different pruning techniques and often perform somewhat competitively to pruning. Yeah. Now, before we wrap up, I want to have a quick discussion about NAS and age of transformers. And actually, this is just the one slide, and it could be much longer. I could waffle around this topic actually for another 90 minutes. But I still think it's important, that's why I want to mention it here. So there's this obvious question, or the elephant in the room is that, okay, how does NAS perform in the age of transformers? And there's, it seems to be the current evidence suggests all the work on scaling laws that scaling is actually more important than model choices, right? So if you want to improve your performance, you just make your model bigger and the data points, increase the number of increase your data set. And that's something then optimizing the architecture essentially, right? And that's not reflected in our benchmarks, but in NAS Bench 2.1 or, or some of the other benchmarks, we always have a fixed model size, right? And the question is, okay, maybe we find the best architecture on this model size, but what would happen if I take another architecture, maybe a random one, and just make it twice as big? It's obviously slower, but performance might actually perform better than optimizing the optimum architecture. So that's, I think, a current problem in the NAS literature is that this whole scaling that's super important for transformer network or for large language models is not really reflected in our benchmarks. And then this question that I always get asked is that, okay, I'm going to find the next transformer by NAS. And my answer is no, probably not. But I don't know, right? And I've been wrong in the past, so yeah, who knows? But the problem that I see right now is that essentially we are somewhat limited by our search spaces, and I think einspace is an interesting direction into that to allow for more complex search space or like more expressive search spaces. But no, I don't think we would be able to find like an attention mechanism or like transformers by NAS right now. Maybe in the future we will, and would be really exciting, but right now I don't see it. It doesn't mean that NAS is obsolete, right? We've seen those applications like hardware-aware NAS, which is a very practical thing. It's maybe not as fancy as like finding like entirely new architectures, but it's a very practical problem. Model compression, I think, is interesting. So, and in the future, I would think it's also worth to combine NAS maybe with other approaches, like distillation, for example. And there's a talk on Friday by Bosch that goes somewhat in that direction. Yeah, with that, I'm almost at time, so I want to wrap up. So conclusions, essentially NAS is an extension of hyperparameterization, right? Or an extension of the general idea of deep learning. That we replace the feature engineering by deep neural networks, and now by the architecture engineering by NAS. And it's the extension of the idea of hyperparameterization where, or a special case of hyperparameterization where instead of optimizing hyperparameters, you only optimize the architecture, or hyperparameters that define the architectures. The different types of search spaces, I only talked about two. There are actually much more. Cell search spaces and contextual full grammar approaches. Then we can write down NAS as a black box optimization problem, and it is somewhat infeasible, but on some search spaces, right now, the only thing we can do. And there are weight sharing based approaches. They're radically different in some sense, but and much more efficient. But then we also saw that they're somewhat limited, right? You can't just go to arbitrary large networks. And it's somewhat limited by the size of the super network. And there's some interesting applications for NAS, which I think are highly relevant, such as finding the optimizing architecture for specific hardware, model compression. And still there is some research going on that really tries to find like entirely new architectures. With that, I'm at time. So thanks everyone, and happy to take any questions.